Yes, children. Let us see now comparison of dipole moment of NH3 and NF3. Now, in the case of NH3, you know very well that nitrogen is more electronegative than hydrogen. And in the case of NF3, F is more electronegative than N. Okay. Now, look at the dipole moment values. In the case of ammonia, it is 1.47. And in the case of NF3, it is just 0.24. In spite of the fact, F is much more electronegative than nitrogen. Now look how the dipoles are shown. Now N is more electronegative, so all the three dipoles are pointing towards nitrogen, and the resultant dipole of all these three is this. And there is a lone pair of electron on nitrogen, and the dipole due to this lone pair, that is called as orbital dipole. So you see here the orbital dipole as well as the resultant dipole, both of them are in the same direction, which is adding up to the dipole moment value. Whereas in the case of NF3, these three are dipoles and the resultant dipole is here and this orbital dipole is this way. And you see they are in opposite directions. Okay, so they cancel out each other to some extent. That is why the dipole moment of NF3 is much less in spite of the fact that F is much more electronegative than nitrogen, right? So that is the reasoning that I have written. In spite of the fact that F is more electronegative than hydrogen, dipole moment of ammonia is greater than that of NF3. This is a very important question. You need to write the key points very clearly, only then you will score. Okay, the resultant dipole in NH3 is in the same direction of orbital dipole. This is your key sentence. Okay, in the same direction, so it adds up. But in the case of NF3, the resultant dipole and orbital dipole are in opposite direction and hence cancel out each other, thus reducing the value of dipole moment. Okay, right. So that is about one particular condition. Now let us see what are the applications of dipole moment. It helps you in determining the shape or geometry of the molecules. If mu is equal to 0, then the molecule is either linear or symmetrical. Okay, either linear or symmetrical. And if mu is not equal to 0, then the molecule is not linear and you can say that it is unsymmetrical. Okay, now mu is equal to 0. Which are the molecules? All these three. We already saw this. Okay, CO2 is linear, BF3 is planar, CH4, CCl4, they are tetrahedral. So they are all having symmetrical geometries and their mu value is 0. Whereas NH3, NF3, water, they all have some dipole moment value. That means it is not equal to 0. And you know very well that they have their own shapes or geometries. These two are pyramidal and this is having an inverted V shape. Then how else this dipole moment help? In determining the polarity of bonds. Greater the value of dipole moment, greater is the polarity of the molecule. And also in calculating the percentage ionic character of a typical covalent molecule. Okay, so that is about dipole moment. You are able to explain the ionic character of covalent molecules. Okay, now we are going to see partial covalent character of ionic compounds. Okay, just the opposite we are going to see. And this is explained by means of Fajan's rules. Now what does it state? When a cation approaches an anion, the electron cloud of the anion is attracted towards the cation and it gets distorted. And this effect is called polarization. Polarization of the anion. And the power of cation to polarize an anion is called its polarizing power. And the tendency of anion to get polarized is called its polarizability. Okay, say for example you have Li plus and I minus. I minus is big. The size of I is very big. And that of Li plus is very small. Right? Now what happens? This Li plus, it polarizes the I minus. With the result, what happens? The shape of this I minus, it gets distorted and it gets converted like this. So, some of the electron cloud of this I minus falls into the positive sphere of Li plus. Is it not? So, what happens? This region gets neutralized. Neutralize होने पे क्या हुआ? Ionic character थोड़ा कम हो गया और covalent character बढ़ गया. Okay. So, this is what we are going to see. See, I have shown the same thing. Okay, Li plus and I minus. So, the electron cloud of I minus is falling into the positive sphere of Li plus, thus getting cancelled. So, a small amount of covalent character is introduced. Okay, that is why we say Li, in spite of being an alkali metal halide, it is covalent. Why? This is because of greater polarizing power of Li plus, which distorts the electron cloud of I minus, thus bringing in covalent character. Okay. Now this polarizing power, it is favored by what? Small size of cation. Smaller the cation, greater is its polarizing power. Large size of anion, larger the anion, greater is its polarizability. An anion gets polarized and a cation polarizes. Okay. So Li is more covalent, Lif is highly ionic. Then large charge on the cation or anion. So this is again another reason. Larger the charge, then what happens? If the cation is having larger charge, then it has greater polarizing power. Okay, that is why you say NaCl less than MgCl2 less than AlCl3. Greater the charge, greater is the polarizing power. So Al is having Al3 plus. The charge is greater. Greater the charge, greater the polarizing power. Whereas here it is Na plus. Here it is Mg2 plus. The charge is maximum here. Okay. So AlCl3 is more covalent than NaCl. NaCl is less covalent than MgCl2. MgCl2 is less covalent than AlCl3. That means AlCl3 is the most covalent. Same way, greater the charge on the anion, greater the polarizability. Okay.